Hey, welcome back. So, in our Mathematics in the Modern World, so Chapter 2 is about mathematical language and symbols. So, mathematical language, it is the system used to communicate mathematical ideas. So, just like the speech, we can communicate using mathematics. Okay. So, out of all the mathematical ideas, there are four main actions attributed to problem solving and reasoning. So according to Kenny, Hanschwitz, Hauer, Metzizo, and Tuttle, there are four main actions. These four main actions are modeling and formulating, transforming and manipulating, inferring, and communicating. Modeling and formulating. So this is creating appropriate representations and relationships to mathematize the original problem. Transforming and manipulating. Changing the mathematical form in which a problem is originally expressed to equivalent forms that represents solutions. Inferring, applying derived results to the original problem, situation, and interpreting and generalizing the results in that light. Communicating, reporting what has been learned about a problem to a specific audience. The characteristics of mathematical language. Number one is precise. So the mathematical language is exact or accurate on delivering its ideas. Concise, it expresses much more on a few words or letters. Powerful, having great influence. Clear, so free from confusion. Unlike the speech, there are different meanings based from what word we use and what emotions are being used. Objective, so emphasizing or expressing things. Mathematical expressions and sentences. A combination of mathematical symbols and operations that convey mathematical ideas. So number one is the basic operations. So we have the addition, subtraction, multiplication, and division. So we have learned this in our elementary days. And we have a variable represented as any letter, but usually we use x and y. So it assumes many values. So we use this to represent the unknown on the problem. Numerical coefficient, or most commonly known as just coefficient, that is the number before the variable. It represents how many times the variable is being added to itself inside a term. Constant, any single number in the expression, it represents a fixed valued quantity. Polynomials consist of terms, which terms is actually a combination of a constant and variables preceded by a minus or a plus sign. So we know that monomial is a polynomial consists of only one term. Binomial consists of exactly two terms. Trinomial is three terms. So polynomials is for more than one term. Mathematical sentence. Combine two mathematical expressions using a comparison operator. So these comparison operators are the equal sign, not equal, greater than or equal to, less than or equal to. So examples of equation is in here. 4x plus 3 is equal to 9. So we use equality as a symbol for an equation. Example is volume of a cone, the equation for finding interest, area of a rectangle, and equation of a straight line. Examples of inequality. So yan. 15x minus 5 is less than 3y. Another one is 2x plus 3y is greater than or equal to 4. An open sentence uses variables whether or not the variable is true or false. Example is 2xy less than 3y. So this can be true or false depending on the value of the variables na gagamitin natin. If x is equal to 2 and y is equal to 3, then 2 times 2 times 3 is less than 3 times 3. So it is actually false because on the left side, this is equal to 12 and the right side is 9. 12 is greater than actually to 9. Closed sentence. A mathematical sentence that is known to be either true or false. So the true closed sentence example is 2 quantity x plus y is equal to 2x plus y. This is actually the distributive property. If x is equal to 1 and y is equal to 2, so substituting the values of x and y, okay, we have 2 times 1 plus 2 times 2 is equal to 2 times 1 plus 2 times 2. So they are equal expressions. So it is true. Another is 6 is equal to itself. So there is no confusion there. It is always true. A false closed sentence example is given that 9 is an even number. And we all know that 9 is not an even number. It is an odd number. The statement is false. Conventions in the mathematical language. Context refers to particular topics being studied. It is important to understand mathematical symbols. Conventions is a technique used by mathematicians, engineers, scientists, and anyone in which each particular symbol has a particular meaning. The four basic concepts. Number one is sets. It is a well-defined collection of distinct objects, usually named with a capital letter. So this can be used in a set of numbers, set of people, set of letters, and etc. So the symbol, this sim so this symbol represents membership. X is an element of A. It reads as X is an element of A, which means X can be found in A. This symbol denotes non-membership, and it is read X is not an element of A, which means X does not belong to a set. There are two ways to describe a set. Number one is roster or tabular method. The elements in a given set are listed or enumerated, separated by a comma inside a pair of braces. Number two is a rule or descriptive method. The common characteristics of the elements are defined. Example of roster or tabular method. The elements of A are as follows. Okay, so the elements of A is separated by a comma and inside a curly brace. Rule or descriptive method. Example, all integers in set B are negative integers. So example, all integers in set B are negative integers. So the common characteristics of the elements in B are being negative integers. Another representation of the same set Okay. In mathematical rule, B is equal to a set containing x such that each x is less than to 0 and every x is an element of the integer set. Okay. Another is B is equal to a set containing negative integers. So these representations are all the same kinds of sets. We have the empty or null, or what we call the void set. Number 2 is finite set, infinite set, and lastly, the universal set. So the empty, null, or void set, it has no element and denoted by this symbol, or a pair of braces with no element inside. The finite set, it has countable number of elements. Example, let x be 1, 2, 3, 4, 5. That's the end of it. Infinite set has uncountable numbers of elements, so it cannot be counted. Example, let x be set of all natural numbers. So the natural numbers are what we use in counting. So we start from 1, 2, 3, and so on and so forth up to infinity. So it doesn't end. The universal set. It is the totality of all elements of the set under consideration, denoted by capital U. Example, given the universal set from 1 to 10, there is a set 1, 3, 5, 7, 9. Set B, we have 2, 4, 6, 8, 10. And set C, we have 2, 3, 5, 7. So we can see here that given all sets, the universal set is the totality of all elements that we are considering. The relationship between sets. Number 1, equal sets, equivalent sets, different sets, and disjoint sets. Equal sets are sets that have the same elements. Example, set A is 1, 2, 3, set B is 3, 2, 1. So since we have the same exact elements, it doesn't matter if it is arranged differently as long as you have the same elements. Equivalent sets, they have the same number of elements. Example, set A is 1, 2, 1, 2, 3, 4, 5. So we have 5 elements. Set B is a set of letters A, B, C, D, and E. Okay, so we have 5 elements also. So they have the same number of elements. Joint sets have at least one common element. Example, set A contains 10, 20, and 30. Set B, we have 5, 10, and 15. So the element 10 is the common element between those sets. Disjoint sets. So they are sets that have no common element. Example, so set A and B have no common element. Subset. It is a set that every element of which can be found on a bigger set. So the symbol, it means it is a subset of, for example, so set containing A, B, and C is a subset of set containing A, B, C, D, and E. Then symbol of subset with a slash means not a subset of. So the set containing A, B, C is not an element of the set containing D, E, F, and G. Improper subsets. If the subset is actually equal to the set itself as a whole. So the set containing 1, 2, and 3 is an improper subset of the same set. Another is if the subset is empty. So an empty set is actually an improper subset of any set. We also have the power set, a set containing of all possible subsets, including the improper subsets of any given set. Example, if we have a set A containing A, B, C, the power set can be shown as the collection of all possible subsets of the set A. So power set of A is a collection of a null set containing A, only B, set containing C, set containing A, B, A, C, B, C, and set A itself. So we have operations on sets. Number one is union, intersection, next is difference, and complement. So union, it is a set whose elements are found in both set A or set B. Example, given set A containing 2, 4, 6, 8, and 10. Set B containing 1, 2, 3, 4, 5, 6. The union of sets of A and B is combination of all elements of both set A and B. So each element of the union can be found in either set A or B. 1 is from B, 2 from B also and also A, 3 from B, 4 from both A and B, 5 from B, 6 from B and A also, 8 from A, 10 from A also. Intersection, a set whose elements are common to both sets. Example, given set A, we have 2, 4, 6, 8, 10, and set B, 1, 2, 3, 4, 5, 6. So the intersection of set A and B is containing all the elements common to A and B. Difference is a set whose elements are found in set A but not in set B. Example, if we have set A containing 2, 4, 6 and set B containing 2, 3, 4, 5, 6, the difference between set B minus A is only equal to the remaining elements in B, removing all elements in A. So we have 3 and 5 only, removing 2, 4, and 6, which is the element of A. Complement of a set A. A set whose elements are found in the universal set but not in a set A. Example. So if we have given a universal set containing 1 to 9, and if we have a set A containing 1, 2, 3, 4, 5, so the complement of set A is all the elements in the universal set but not in set A. So we only have 6, 7, 8, and 9. So the operations on sets can be shown by VENN-EULER diagram, or what we call the Venn diagram. It is a pictorial representation of relationship and operations of sets. The union of A and B, the shaded region is what is included in the union of the sets A and B. A intersection B, so only the overlapping region is shaded. A minus B, so the shaded region is inside A but not in B. A complement, so it is the shaded region outside the set A. Number 2 on the basic concepts is the functions. It is a rule that assigns each element in X or set X to exactly one element in set Y. So for example, a student-subject pair. So set X composed of students and set Y composed of subjects. So the result is now what we call the ordered pairs and in the form of X, Y. So we have the ordered pair set containing the ordered pairs, Alisa and chemistry, Elijah and math, Steph and physics, and statistics. Number 3 is relation. It is a rule which associates each element of the first set with at least one element in the second set. So we say at least, so we associate each element of the first set into any number of elements in set B. Functions and relation. In short, in function, one input is equal to one output, or it is 1 to 1. For example, so we have each element on first set is associated with only one element on the second set. In relation, one input can be paired into many outputs. So it is a one to many. So here, one of the input is paired with more than one output. Lastly, we have the binary number system, a number system that only uses two numbers, 0 and 1. So in order to use the binary system, you must be familiar with this table. Using a base of 2, meaning there are two numbers that is being used. So for finding its decimal value, 2 raised to 0 is always equal to 1, and number raised to 0 is 1. 2 raised to 1 is 2. 2 raised to 2 is 4, or we can just multiply each decimal value by 2. So we have 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, times 2 is 16, times 2, 32, times 2, 64, and so on. Converting decimal number to binary, so we divide the whole number by 2. If there is any remainder, we will write 1, and if there is no remainder, we write 0. And repeat dividing the whole number by 2 until the last possible value for the whole number is 1. Example, convert 142 to binary. 142 divided by 2 is 71 without a remainder. 71 divided by 2 is 35 with a remainder of 1. 35 divided by 2, 17, remainder 1. 17 divided by 2 is 8, remainder 1. 8 divided by 2 is exactly 4 without a remainder. 4 divided by 2 is 2 without a remainder. 2 divided by 2 is exactly 1 without a remainder. And 1 divided by 2 is equal to 0 with a remainder of 1. Then we will read this. We start with the most significant byte up to the least significant byte. So 142 in binary is 1 0 0 0 1 1 1 0. Another technique is we memorize this table. So 142 can be shown in this table. Okay, since 256 is greater than 142, so we won't need 256. And 128 is less than 142, so we can use the value, then we can throw it as 1, meaning it is being used. Then we subtract the value of 128 from 142 since we already used it. So what remains is 14. 64, 32, and 16 exceeds 14, so we cannot use it, so they are 0. Then 8 is less than 14, so it is also 1. Then we subtract 14 minus 8, what remains is 6. Then we have 4 is less than 6, so it is also 1. Then subtract 6 minus 4 is equal to 2. Then 2 is equal to 2, so it is also 1. 2 minus 2 is exactly 0, so there is no more remainder, so the rest would be 0. Therefore 142 in binary reads as exactly on the table 1 0 0 0 1 1 1 0. Conversely, we can convert binary number to decimal. So converting 10111010 into decimal, so with the same process, we will input all the place values of each binary number into the table. So we have 10111010. Okay. So all numbers with 0, we will not use them. So we have 64, 16, 8, and 2 only. So getting their decimal values, adding all of them, we had 64 plus 16 plus 8 plus 2, and we have a decimal value of 90.